Hello, everyone. My name is Nicholas Tercios. I am joined today with Andrew Moffat, and today we will be discussing the collaboration between multiple UAVs for fire detection and suppression. So for a quick overview, we will first start with what motivated us to start this project, how we saw many problems with methods that are currently employed in our proposed solution. From this proposed solution, we will talk about objectives we had for this project this year, going into the concept of operations that we wanted to be able to perform at the end of this year. Going into that, we will discuss some of the flight hardware, including the UAV itself, some of the sensors on board, and our suppression mechanism. After this, we'll discuss the detection and location algorithms, transition into the flight planning that allows this entire operation to be autonomous. We'll discuss all the testing and results we collected, and then move into our future work. The motivation for this project was quite simple. Andrew and I are from California, and we have many wildfires during the summer. As such, we are very interested in what detection and suppression methods exist in order to keep our homes safe. As a result, we've noticed that many of the detection and suppression systems in place are either inefficient or can be very dangerous for the crews that must operate them. For example, for ground-based systems, they have the potential to suffer from limited range and can pose a danger to operating crews. While there are satellite-based systems, these systems are very expensive to operate and can have too low resolution to provide accurate spread data or just lack of information to provide. For manned aircraft-based systems such as helicopters or planes that fly over with retardant, these vehicles are expensive and can have large turnaround times in the event that the vehicle misses, making them unsuitable for real-time monitoring, surveillance, and suppression. We propose a safer, low-cost solution is necessary for fire detection, surveillance, and suppression. Our proposed solution is to use UAVs with remote sensing techniques to provide a low-cost alternative platform for fire detection. UAVs can be constructed for high endurance, which would allow them to be capable of tracking and monitoring fires continuously for long periods of time. On top of this, because of the versatility of a UAV, these UAVs can be positioned in desirable locations that can help specialize the real-time data that operators would be interested in. And last but not least, these UAVs can be acting autonomously to sense and track fires, eliminating the need for a human operator. Collaboration between multiple UAVs can effectively be used to detect and suppress fires in large areas. At the same price of a typical helicopter-based system, a fleet of UAVs can instead be used to detect and suppress fires in an even larger area. The objectives we had for this year were simple. We wanted to develop a UAV capable of identifying and tracking fires. We also wanted to generate a method to locate these detected fires rather than just saying a fire exists. We wanted to have the ability to provide latitude, longitude, and altitude coordinates for the fire. At the same time, we wanted to develop and integrate a suppression system onto a UAV. Last but not least, we wanted to verify our design via extensive simulation and flight testing. Here's the concept of operations. This is an example of a mission we wanted to perform at the end of this development cycle. We would start with the detection UAV having a manual takeoff. The reason for the manual takeoff is due to the fact that there are many important sensors on board and we would want to ensure a safe takeoff at all points. From here, we would switch to a guided mode that would begin to autonomously navigate a search area that would be pre-described. As it's searching this area, it would have to avoid potential obstacles and scan the surrounding area with its IR sensor to detect fires. Once it has a ping on the fire, it'll store the geolocation data and return to the launch, where it'll be switched to a manual landing and land. From here, we can take the geolocation data, processes other fire data, and then upload this geolocation data into the suppression UAV. The suppression UAV, similar to the detection UAV, will have a manual takeoff, which will go to the location in question where the fire is located and deploy a suppressant. It will then return to launch and land. Again, this is a simplified mission, but this is the mission we aim to go for now. And if we can get to this point, then we believe that the next logical step would to be the fleet we described previously. So now we're going to delve a little bit more into the flight hardware, starting with the UAV platform. The UAV platform that we used for this mission was the Matrice 600. The flight controller it used was the A3 flight controller, which is capable of autonomous waypoint navigation. Some other specifications about the Matrice 600 is it has a flight time of 35 minutes when it's carrying no payload, and a flight time of 16 minutes when it's carrying its max payload of 6 kilograms. It has, again, a payload capacity of 6 kilograms and can travel at a top speed of 18 meters per second, making it ideal for a fast response system that can linger in the air when in a detection mode and then quickly navigate to a fire location during a suppression mode. For the sensors on board, we first start with the Intel NUC processor, which is an onboard computer. This will capture and store all IR camera data. Speaking of the IR camera, we will be using an FLIR tau thermal camera to detect thermal signatures. For obstacle avoidance, as previously mentioned, we'll be using the VLP-16 LiDAR. On this slide, we can see the different mounts that were fabricated in order to attach these systems onto the matrice. On the left, you can see the bottom mount, which has a rail system that would attach to the very bottom of the Matrice 600, and this holds the IR camera, Intel NUC, a lithium-ion battery, and appropriate adapters. For the top mount, we have the LiDAR, which would be used for obstacle avoidance. Our suppression mechanism for this project was quite simple. We used a simple Bambi bucket design, which is mostly seen on helicopters. The reason for the Bambi bucket was due to mechanical simplicity, which would allow us to maximize the amount of suppressant we could carry on board. As for the suppressant we chose, we used the water, and this gave us a carry capacity of 1.2 gallons, or the 6 kilograms we wanted to work with. Moving forward, we will now discuss the fire detection and geolocation algorithms that we use to autonomously detect fires. First, we start with the heat detection algorithm. As you can see in figure 1, this is live footage of our IR camera. Figure 2 shows a singular frame from this camera. For each frame, a signal is generated that is run through a high-pass filter and high-pass variance. The intensity is found from these frames as the sum of total number of pixels that range from 200 and 255. As we do this for every pixel, the video will have a variance. We want to find drastic changes in this variance or high variances. At the same time, we want to find the sum of pixels from 200 and 255. A higher concentration of these particular pixels would indicate a fire. So as we look in figure 4, this is a histogram of the pixels that are available in the still. As you can see, the red box indicates the number of pixels between 200 and 250. Going into figure 6, we can see the number of pixels from 200 and 255 along the frames and how it varies. And in the bottom right in figure 7, we see the variance. For this slide, we compare a non-fire and fire situation. The non-fire starting in figure 8, 9, and 10 shows a lower intensity and lower variance, especially that is less drastic. Looking at figures 11, 12, and 13, we can see that a no fire to fire situation has a low intensity to high intensity. Figure 12 showing the red box where there is a sudden spike when the fire appears in frame. At the same time, we see that the variance is very high and drastic. Again, looking at 13, the first few frames do not have any jumps, and then a large jump occurs when the fire is in frame. To verify that there is a fire here, we want to verify what we consider the 5,000 threshold. The 5,000 threshold is a threshold where we count the number of pixels that are above or that are in the range of 200 and 255. This number is derived from the resolution of our camera. After we determine that a fire exists, we want to find the location of this fire. This is as simple as transferring from the camera fixed frame into our body fixed frame. And then we will transition this body fixed frame into the NED frame, which features north, east, and down coordinates. We need to take into consideration the focal length of our camera and which points that we want to project into the NED space.
To help the UAV navigate hazardous environments, 2 obstacle avoidance algorithms were explored as a way to help the detection drone construct a safe flight plan. The UAV is running 2 algorithms during flight to minimize the chance of a collision, a path planning one and a reactionary avoidance algorithm. This slide will discuss the primary path planning algorithm, which is a LiDAR-based edge avoidance algorithm that was previously developed in a prior project on a different UAV platform. It takes points generated by the VLP-16, which is the LiDAR previously shown, and constructs a wall obstacle as seen in the image in the center. The algorithm then solves for the shortest path that the UAV can follow. This algorithm was tested in simulation as seen in the GIF to the right. In this GIF, the cyan dot represents a simulated UAV, which follows the red dot, which is the output from the algorithm, to avoid the black dots, which are the LiDAR points, to a goal represented by a green dot. While the algorithm itself was verified as seen in the GIF, the next step was integrating it with the UAV to flight test. The original plan was to use DroneKit, which is an open source library that can control UAV movements through Mavlink. However, this resource only worked with Pixhawk and other Mavlink compatible flight controllers. And deep into the project, it was found only the DJI A3 controller would be able to be integrated with the M600 UAV. This prevented flight tests in the short term, but we hope to either work with the A3 flight controller libraries or change the flight controller entirely. The second algorithm is reactionary, which means it does not construct a path, but rather backs the UAV up if there are any obstacles in the way. It was determined that this algorithm needed to be developed after testing with the original path planning algorithm revealed that its recalculation rate was too slow. Currently, it is about 1/10 of a second for each refresh. However, this is expected to improve as the method used for processing LiDAR data is a little inefficient. The continuous algorithm has been integrated with DroneKit, and while it ran into the same aforementioned flight controller issue, initial simulation runs seem promising. Ongoing work includes safely coordinating the algorithms together and obtaining a method to control the UAV using the algorithm's outputs. Now we will be discussing the test results we got from both flight tests and ground tests. The first test was a ground test for the fire detection algorithm. As you can see from the images to the right, this was taken from a rooftop looking down at a fire pit that was roughly 5 feet squared. This was to validate the fire detection algorithm's ability to identify a heat source. As you can see from the images in the bottom left and top right, the binary image generator successfully generated an image that cropped out all of the cold spots and only looked at where the fire was. Additionally, the area filter that was previously mentioned was able to cut out all the noise and isolate the fire for the geolocation algorithm. The geolocation algorithm used the data collected from the previously mentioned ground test to identify the position of the fire relative to multiple different angles of the IR camera. As you can see from the image to the right, the location 1, location 2, and location 3 represented by the blue dots all represent positions where the IR camera looked at the fire from. The triangles at the bottom represent the calculated distance values that the geolocation algorithm outputted. And as you can see from the results, the error for the first two locations is around 5%. However, the error for the third location is much greater. Possible sources of this final position error could be wind or errors from the imaging giving the incorrect position of the fire inside the frame. The fire detection algorithm was tested multiple times also in a flight test from a variety of different altitudes and positions. As you can see, we used the same fire pit from the ground test, only this time we were looking down at a 40-degree angle from the Matrice 600 platform. We also, in addition to looking at the fire pit, looked for people as well, so that the algorithm could be verified against both a hot target and just a warm target that wasn't a fire. The fire detection algorithm successfully was able to identify fires and people as hot sources and isolate them. In addition, the flame detection that was mentioned previously was able to tell the difference between open flames and just a warm body. As you can see from the image on the right, we also looked at heat sources from the IR camera as an alternative to looking for flames, as this wouldn't detect pure flames, but only sources of greater than about 300 degrees Celsius. Some issues that we ran into were identifying fires at high angles of attack was difficult for the flame detection algorithm, because as you can see from the image, at such a high angle of attack, you are no longer seeing the flames, but rather just a hot mess, making it difficult for the algorithm to identify what was a fire and what wasn't. We also tested the geolocation algorithm during the flight test using the same IR camera data used in the detection mission. Our calculated value versus value was off by about 3 meters, resulting in an error of about 28%, which would have resulted in the suppression mission missing the target that we had put out there. In an actual fire, this might have still hit the target, as they tend to be much larger than 3 meters, but we still want to work on reducing that large amount of error. It should also be noted that this error of 28% is much larger than ground test error of about 5%, meaning that this source of error most likely is coming from something specific to the flight test. Some potential sources of this error are accounting for the position of the camera relative to the UAV's GPS location, or accurately syncing up the camera's position with the IR camera's output. Lastly, we tested the suppression mechanism. We performed 3 separate bucket drop tests, releasing about 1.2 gallons of water at a UAV altitude of roughly 20 feet, or a bucket altitude of about 10 feet above the target. The amount of water we dropped was enough to extinguish the flames of the 5-foot squared fire pit and reduce it to only embers. However, one test we performed resulted in us missing the fire completely, despite the UAV being at a low altitude and in the correct position. This is because we had not accounted for wind, and it simply blew the water over the fire and onto the ground next to it. It should be noted that actual fires tend to be much larger than the fire pit we chose, meaning that wind may not play as large of a factor that we initially thought during the flight test. However, we still want to look into using maybe some predictive wind to mitigate this problem, or redesigning the mechanism entirely. Finally, we will discuss future works of the project. Going into the future, the biggest things that we want to test are validation and further testing of our geolocation algorithm and fire detection algorithms that we have mentioned. We also are thinking of adding in LiDAR mapping. This would work in tandem with our current LiDAR sensor and IR camera to give firefighters on the ground a better image of what's going on around them. We also want to look into inter-UAV communication or swarm technologies. This would allow us to run more detection UAVs to get a better sense of the fire, or run more suppression UAVs. As seen in our flight test, one single UAV dropping about 1.2 gallons isn't as effective as potentially multiple UAVs all dropping continuously over a long span of time. This will hopefully make the system just as effective as other firefighting systems, or better. We also want to evaluate the possibility of combining both the detection and suppression UAV into a single configuration. And then lastly, we want to develop and expand our schedule and budget into the following years, with also expanding our team size to help us spread workload and add more capabilities onto our firefighting drone. We would like to finally thank Lockheed Martin for their continued funding and support and feedback for our project. We also like to thank ICUAS for this opportunity to share our research and work. Thank you.